Good morning, everybody, or good afternoon, good evening, good night. So this session's about neural networks, and neural networks are incredibly powerful things for dealing with almost any complexity of data that you have. Given enough data and enough computer power, neural nets should be able to what's called approximate any possible function of inputs to outputs. In mathematical language, in human language, neural nets, given enough information and compute power, should be able to learn anything. If it's learnable, neural nets should be able to learn it. They're very, very powerful things. So, and we're going to look at it using the Titanic example, and neural nets are completely over the top, arguably, for such simple data. But it's an easy to use data environment that we're all slightly familiar with, hopefully, by now. So we'll kick in with the Titanic data set. First off, you don't get far into neural net world without people starting to talk about GPUs. So let's just quickly address what they are, why you might want one or access to one, and where you can get them. So GPU is graphical processor unit. They were designed very much for video gaming on computers, handling large images, video, at a single time and being able to sort of manipulate that whole image at once. They also turned out to be very, very handy for many neural nets, in that neural nets can require doing tens or hundreds of thousands of calculations for the same data case as it passes through, as you go through all your data cases. And actually you can bundle a whole lot together and pass all of that to a GPU, and it kind of does it in one calculation step and then puts it out. So GPUs are massive parallel computing units that you can have in your computer. Now, compared to your normal computer processing unit, which is called a CPU, it's a bit like a heavy goods vehicle versus a fast motorbike, in that you don't want to use GPUs for all sorts of things, because actually it takes quite a long time to get all the data onto the GPU. It then crunches it very quickly, but then you have to get it out again. So they're not brilliant at everything, but they're brilliant at some things. And if you get into neural networks, it's quite handy to have access to one. Now, you can either buy a computer with one, and now you can get quite sleek computers, because they used to be sort of big things. So anybody who's looking around, I mean, that's a Dell XPS 15. That's got a fairly decent GPU in it. So if you're looking for a laptop capable of doing neural networks, that's, I think, one of the best choices around at the moment in terms of still being portable, but having the GPU unit in it. Or all sorts of workstations, desktops, you can order with GPU. You do want, so just on the technical bits, if you're getting this equipment, NVIDIA GPUs, not AMD. Because NVIDIA GPUs are what people write neural net stuff for. Anyway, that's GPUs. For today, but Titanic you can deal with on an ordinary computer. But we'll also look at Colab in a second, Google Colab, where you can do compute in the cloud, and you have, at the moment, free access to a GPU as well. So let's look at how we're going to run our Titanic environment today to enable use on a GPU if you want it. Okay, the notebook we're going to work through today, you can either work through locally or work through on the cloud, which I'll do as we go along. If you want work through it locally, it's in the Titanic GitHub repository, which I'll link to below, and just make sure that's refreshed to make sure you've got this workbook. And I'll mention instructions about installing TensorFlow, which we'll use today. But if you followed instructions on the previous video on installing an environment locally from a YAML file, that automatically installed installed TensorFlow for you as well. Okay, but let's go in. If anybody wants to do this on the cloud, and on Google Colab, we'll also select running on the GPU, which will make it a bit faster. So pythonhealthcare.org, and then just below the title I'm going to click on Titanic Survival Machine Learning. Okay, so below the picture of the Titanic there's a link to the GitHub repository. So this contains all the code. So if you wanted to download this, you go to the big green code button, click, and you can download as a zip there. And then in the README we can launch on Binder, which I might remove actually, or opening Colab. Definitely for this, don't use Binder, it'll be far too slow. Click on opening Colab if you want to run on the cloud. You will need a Google account. So we're going to click on opening Colab. This opens up a bit of an ugly file manager, and I'm going to scroll down. It's in alphabetical order. I'm going to scroll down to right near the bottom. If you drag it right to the bottom, I've got Jupyter Notebooks, HSMA, neural nets, and I'm going to click on that, and this opens it up in the cloud on Google servers, which at the moment is free. Okay, before we start running, we just want to select our GPU environment. If you're doing anything with neural nets that you're batch processing any data, use a GPU if you've got one available, and it's under runtime. So right at the top, underneath the title HSMA neural nets, there is File, Edit, View, Insert, Runtime, Tools and Help. Click on Runtime, then change Runtime Type, and change the runtime type to Hardware Accelerator to GPU. Below that there's TPU, which you can try as well. They're relatively new, they're tensor processing units. They're GPUs designed specifically for tensors, which are multiple dimensional matrices, which we use in machine learning. They're fairly new. If anything, they're kind of like stripped down GPUs without all the gamey stuff that you just don't need for machine learning. But I would probably stick with GPU and then save. Okay. So if you want to install TensorFlow locally, you can either create the Titanic environment, as in the instructions last time, or you can create a new Anaconda environment, and this line here, conda create an environment, n, give it a name, the name is TensorFlow, and then after that, if we put TensorFlow again, it will tell Anaconda you want to build a TensorFlow environment. It's got kind of Anaconda knows what to do with that. And then install, you can do this on a separate line as well. Maybe in Windows you might have to. I'm not sure if the double and, which means if the previous step works, then carry on and do the rest. If you're using Anaconda command line in Windows to do this, you might want to do conda create TensorFlow first, and then on the second line conda install, and then into which environment, TensorFlow environment, scikit-learn, pandas and matplotlib, because I'm not sure those come automatically with the TensorFlow environment. Or you can set up locally, and just in any environment you're in, you can either do conda install TensorFlow or pip install TensorFlow, and that will install it in whatever environment you're in at the moment. Okay, so that's a bit about running it, but we're going to run it on Google Colab here. Okay, so I've just found a limitation of Google Colab is that it doesn't show images that should be in the notebook. So I've switched to a local copy here, and that you can see as I talk through this. If you want to look at them, I'm afraid you'll have to open a local copy, it seems, of the notebook to get them. So what we'll talk about now is the basic building block of neural networks. Which, if you follow through with logistic regression last time, is going to be actually very similar. So the basic building block of a neural network is a neuron, or you might sometimes hear them called perceptrons, which was their original name given to them. And so a neural network in scikit-learn is actually called a multi-layer perceptron, and it's a multi-layer perceptron, and neural networks are the same thing. So let's have a look. They were invented, if you like, by Frank Rosenblatt, who was a psychologist, neuroscientist, but also with an interest in computational modelling, to try and mimic the behaviour of human neurons. And then the idea was that he was going to put them together. Well, in fact, he did put them together, kind of literally wired together. So the basic building block of a neural network is that we have our input features. So this would be taking our original data, if you like. So for the Titanic, this would be age and class or fare. One that says, are you male? Another one that says, are you female? And so those are our input features, and then each of those input features goes into our neuron, if you like, and each of them has a weight, or statisticians might call them coefficients, but now we're into neural networks, we're going to always call them weights. And the weight for each is individualized for each feature. And we also have what's called a bias, which gives us a sort of constant shift, if you like. And we mimic that by just creating an extra, or it automatically does it, a dummy feature with the value 1, and we have a weight for that. Now the neuron or perceptron will take each of the features, multiply it by the weight for that feature, and add them together. So this is our weighted sum. So it takes feature 1 multiplied by weight 1, then adds feature 2 multiplied by weight 2, then adds feature 3 multiplied by weight 3, etc., etc. Adds them up. To begin with, these weights start out completely randomly. We'll look at how they learn and optimize a bit later. They get added up to weighted sum, and then the weighted sum is passed through what's called an activation function. It does something with this weighted sum function. Now, in Frank Rosenblatt's original work, the activation function was very simple. It was what's called a step function. If the weighted sum was below a certain value, the output would be 0. If the weighted sum was above a certain value, it would be 1. So that mimics, kind of, for him as a neuroscientist, it mimicked a neuron that was either active or not active. We don't use simple step functions anymore, but that's sort of is the simplest example. And then we get an output, which is y, which it could be a classification. Is this a dog or not? Or it could be, for activation it would be a step activation, it would be a sort of some kind of classification, are you one thing or another. And then the principle of neural network learning is that we have an error, were you right or wrong, and how much were you right or wrong by, and that feeds back in a way that the weights are updated to try and get you closer to the right output. We'll look at this in a bit more detail. This is the way it's machine learning. You give it a whole lot of labeled examples where you know the features, you know the output, and you train it such that the network adjusts its weights, and here it's very simple, and it shuffles those around in order to minimize the number of times it gets it wrong on your training set. Then once you've trained, then you let it go on a test set or out in the real world. So that's the training, the learning process. Okay, so that is a neural network. Take your feature, or sorry, that's a neuron, the building block. Take your inputs, so features here, multiply each one by a weight specific to that feature, add up all of those together, pass it through an activation function, and get your output. And then that is the building block of neural networks. Okay, so how do we build those up into a neural network? Well, quite simply really. Each neuron is exactly as above, but we then just in one layer replicate the number of neurons. So before we had one neuron which had inputs from every input layer, and then it had one output. Well, now we have here 4 layers. These are called hidden layers as well, because they're kind of, well, in the middle of the network. Each input now goes to 4 neurons. And in this case, we have a second layer of neurons. Again, just 4 here. And the output, so we've done a weighted sum, we've passed it through an activation of some kind, and the output goes to each of the neurons in the next layer. This is called a fully connected network. We'll look at some other slightly different examples in a bit. Each neuron is exactly as the perceptron. It adds up its inputs. Each of its inputs will have a weight particular for that neuron and that input feature. So each arrow here will have its own weight. We add those up, pass it through an activation function, and then it goes out. And then in our final layer, well, our final hidden layer here, they're each outputting to a final output layer, so which is a single neuron in this case. Doesn't have to be, but if you were trying to do a binary classification, did this person survive or not the Titanic? Are you likely to be admitted into hospital, yes or no, or probability of? You pass it into a single output neuron. Then that does the same. It sums up the inputs, each multiplied by its own weight, and then that passes through another final activation function to give you your output. And we'll look at the different kinds of activation functions in a second. But that's the neural network. It's very simply lots of... The principle is simple. It gets complicated, you can see, but the principle is you build up multiple neurons, each take all of the inputs, multiply them by their own weights, sum them up, and then the output goes through an activation layer and to all of the neurons in the next layer. That is a neural network. Okay, activation functions. So what do you do on each neuron with the output before passing it on? That's what your activation function does. The activation function can be different for every single neuron. They tend commonly to be the same throughout much of the network or blocks of the network, and then you might have a different one at the end. Let's have a look at some common ones. So it's still called an activation function, but we could effectively do nothing with the output. We could just leave it completely unchanged, in which case we call that a linear activation. So we still, for the sake of consistency, say there's an activation function there, but that activation function doesn't change the output. So it adds up the sums, the weighted inputs, so each input multiplied by each weight, adds them up, and then just passes it out straight away. That is often used as the final output for regression problems, so trying to predict, say, house prices, or if it's a continuous variable, you're trying to predict a number rather than a classification. Your final output will normally, your final error will use a linear output. Step we described before, it's just based on the value of the output, you give it 0 or 1. It's almost never used. Probably could say it's never used, but there for completeness because it's there in history. Now the sigmoid function scales the output from 0 to 1 using a logistic function. So remember from the logistic regression, we converted a sort of continuous output into 0 to 1 using the logistic function. Here, the logistic function is, in neural net world, is normally called sigmoid activation, which is nice because it's nicely descriptive. And the sigmoid activation gives you a sort of sigmoid S-shaped that goes between 0 and 1. And it tends to be used where you want a probability output for a classification. So that's where you'll come across the sigmoid most. Can be used inside the network as well, but tends not to be so much these days. It tends to be used in the output layer and converts 0 to 1, converts the output to a probability. Tan-H you may come across, and it's similar to sigmoid, except it scales it from -1 to 1. It was common in the early days of neural networks, so you might see it around from that. It's not used very much now. ReLU, on the other hand, is used massively around the place within the network itself, and it's an incredibly simple activation function that, if the value is greater than 0, it keeps it. If it is less than 0, it sets it to 0. So effectively removes the input and sets it to 0. Now that very simple function is sufficient to enable neural networks to model very complex non-linear functions. You've got to have some kind of non-linearity, so something that doesn't just convert the output, has a sort of directly proportional to the inputs in the network to model non-linearity. And it's in a way remarkable that this very simple function does that. However, you might see some modifications of it used around the place. One is called leaky ReLU, and rather than being 0, always 0, if your input to the activation function is less than 0, it gives it a very shallow line. So it does produce negative outputs, but the negative outputs are very compressed compared to the input negative. So that's a leaky ReLU. See, this line here just starts to dip below the axis. And then similar to that is the exponential linear unit, the LU, and that does kind of a similar job there, that we have a slightly more complex relationship around for for negative numbers. So, I mean, the thing to do, start with ReLU within all your networks to begin with, I would say, and then you might want to try leaky ReLU or LU. Max out is more complicated, it allows a more complex function to be built, activation function. It's not an activation function I've used or any experience of, so can't really comment on that. Standard one is use ReLU in the network to begin with, and then probably, if you're looking at probabilities, sigmoid output for a probability. If you got multiple classifications, say dog, cat, bird, you want the probability to add up to 1 and say, well, look, there's a 90% probability this picture is a cat. an 8% that it's a dog and a 2% that it's a bird, for example, then use a modification of the sigmoid called softmax. There isn't a picture of it here, but softmax will give you a normalized probability outcome where the total of your output values will be 1. And you shouldn't normalize probabilities, so you shouldn't add up a whole lot of probabilities and convert them and then normalize them so they add up to 1 directly. You should do it via the softmax function. Okay, so we've got our neurons. We've looked at, they all create a weighted sum of their inputs. They then all pass through an activation function that modifies that in some way. The next thing we need to look at, all these you're going to select. When you build a neural network, you have to tell it which activation functions to use. And the other thing a couple of things we want to look at. Next one is what's called the loss function. And the loss function is how the neural network calculates how wrong it is. Because that's needed to be able to pass back and modify the weights in the neural network itself. And there are various loss functions, but there are 2 common ones which you'll be using. The first is the mean squared error loss, and this is used for continuous variables if you're trying to predict, house prices or length of stay of patients, something like that. It's simply you take the predicted value, look at the difference between the predicted and the observed value and square that, and then you add that up for all of the examples you're looking at. Then the other one is cross entropy loss, and this is the loss that you use for classification networks. So if your job is to say, did somebody survive or not survive, or you think they would survive, not survive, if you think somebody is likely to be readmitted or not, or if it's you're trying to classify things as cat, dog, bird, etc., then you go for a cross entropy loss. So there are the two key ones: mean squared error loss for regression, cross entropy loss for classification. You'll see something called binary cross entropy loss, which is just if you've got a classification that's 0 or 1, 0 to 1 at the end. Like we're going to use survival or not survival, you'll use something called the binary cross entropy loss. Just sort of says that there's only one of these, essentially. Okay, so that's loss functions, and that's really all you need to know, those 2 common types. Okay, backpropagation optimization. You don't need to know much about this apart from the common optimization engines you can choose and that you'll see around. But just to say, backpropagation is the process by which the neural network takes the final loss, the error, if you like, and it distributes that throughout the network to say, well, how much did you contribute to the error? And that's needed for the network to then adjust the weights in the network in the right place, in the right direction, to be able to sort of close the gap between what it predicts and what it actually is. And there's a couple of videos, YouTube videos here, if you want to see more on backpropagation. Neural networks existed a long time before they were widely used, and it was because for a long time nobody could find a way of effectively training them. But it was Geoffrey Hinton who proposed and developed backpropagation, which was the first time they could be trained well, and then neural networks from then just kind of exploded. But it wasn't, if you find this difficult or hard, if you look at it, don't be surprised. It wasn't, for a long time, nobody thought of it. But the principle is just to apportion error in the right places in the network. Now, optimization we need to care about a bit because we actually set what the optimizer is. And the optimizer decides how much to adjust each weight in the network and in which direction, based on the backpropagation of error in there. Now, there are many different optimizers. You probably ought to be familiar with just 3 that you'll see commonly used. Stochastic gradient descent is kind of like the grandfather of it all, and it basically adjusts the weights according to how much the output changes if you adjust the weights, and it makes bigger steps when you're further away from an optimum, if you like, and as you get closer to an optimum it makes smaller steps. So that's gradient descent, and that principle is used throughout, but this is the kind of raw version of it. There's a danger that it can get trapped in local optima such that it thinks it's found the best, but if it had carried on changing more it would have found another better value of the weight, and so that can be modified stochastic gradient descent by something called momentum, which just keeps it trying to explore more, so it doesn't get stuck in local optima. I've put a link to a couple of videos, more details on this. So you might see that used. RMS prop is a classic benchmark. It was used in the training of for a long time, neural networks. And so you'll see that used quite often, and you can select that if you want to try a classic one. Where most people would start though is with what's called an adaptive optimizer, and the most common one is Adam. So if in doubt, set your optimizer to Adam. Always begin with Adam and maybe try RMS prop if things aren't working too well with Adam. I won't say more about those. You can watch this top video goes through some of the common optimizers, and this short video, it's less than 2 minutes long. The top ones I think is about 20 minutes long. This short video, the second one, is less than 2 minutes on what momentum is. Okay, so that's backpropagation, which is how it's adjusting its weights, because they start off random and then they slowly improve to get a better fit, and then the optimizing, which you'll see we'll select. Okay, so let's go on now to a bit more sort of practical for a second of what we do to train our network given that. And the training process consists of passing your data set repeated times through the network to get it to improve each time. And this is called an iteration. So if you go through the data, pass the data through once, that's a single iteration. But normally you'll need at least 10 and maybe hundreds of iterations, could be thousands, but it's going to do this automatically for you. So there are 3 phases, if you like, in training a network, and the first one is what's sometimes called a forward pass. You provide the inputs to the network and you get the predicted output Y. So we have our predictions from our features. We then calculate, or the neural network engine calculates, the loss between the predictive and the observed. And then when that loss has been calculated, that loss needs to be backpropagated through the network and the weights updated. Now we're going to use TensorFlow, which will do that all in a single step. The other common network that's used in PyTorch, I mentioned these as two separate things because you will do a backward pass through the network and then update the weights as two different steps. Okay, so we have those steps and we basically repeat that each iteration, passing the data through, getting the loss, backpropagating the loss, updating the weights until we reach maximum accuracy, or we reach a maximum number of iterations that we've said. The thing we need to be careful of, though, is as we look, as you train neural networks, they become overtrained to the training set, and you'll start to find, and we'll see, that the training set accuracy can increase and increase, sometimes up to literally 100%, but your test set accuracy starts to drop. The network has become overfitted, and we'll look more at overfitting to the training set rather than being generalizable across all data points. Okay, last bit of theory-ish stuff, but this is useful to know because a couple of questions is how big should my network be and what type of architecture should it be? And it's useful to have a quick overview of those two questions. So at the moment we've talked about fully connected, that all the neurons are connected to each neuron in the next layer, and they're very common throughout a lot of the neural networks, and we'll be using fully connected today. So one of the questions then is, well, how big should the layers be and how many layers? And to begin with, in more the early days of neural net architecture, you saw sort of fancy designs of them, the layers getting bigger and then coming back. Now you probably more commonly see all the layers are the same size, more commonly, apart from the final layer, which fits the type of output that you want. And one of the reasons for that is that it then becomes very easy to just sort of say, well, I'm going to test how many neurons I put in a layer and how many layers. Becomes easy to write if they're all the same. And I believe it's also been shown that generally works well. So you can think of the neural network architecture as being sort of square in the middle of it. Now, as a rough guide, you want to increase the complexity of the neural network, so number of layers or number of neurons, until the model overfits. We'll look at overfitting. So overfitting means that you're getting significantly better fits on the training data than the test data. And to begin with, you want to design a model that does overfit, because at that point you're pretty sure it can deal with all of the complexities in the data, and then we'll use some techniques of then avoiding that overfitting. But to begin with, see if you can overfit, because that's a good start, and then look to control, which we'll look at. Okay, so that's the how big, how wide. You just empirically try until it overfits. So let's look at the architectures, just mention some of these, more the names and what they're used for. So fully connected, we've talked about, very common architecture block that you'll have in most neural nets. Next one you'll hear about is convolutional neural networks, CNNs. You can think of those as kind of like if you're looking at an image where they're most often used, you can think of it almost like a sliding window that steps across the image, then down a bit, and steps across the image again, and it's looking for patterns, say something that looks like a face, in all of the little blocks of the neural network. What they tend to be is the early ones in a network, kind of just trying to identify lines. Is it a straight line? Is it a horizontal line? Is it a full block? Is it a diagonal line? And then subsequent layers start to sort of build those features together to say, this looks like a face. Or so convolutional neural networks, common in image analysis, or the other thing in forecasting. You could look for it. It could basically scan across the forecast looking for what is essentially a fingerprint anywhere in it, but it's the same fingerprint it's looking for everywhere, and then it gives an output. Recurrent neural networks, RNNs, they introduce a sort of concept of some limited form of memory into the network. So any one time, the output of the network is dependent on a number of series of input steps. So where this is important, things like language processing, that you need to work out what the sounds are and maybe the phones, the individual sounds we make, how do they form into a word. So you need some kind of memory in there, and that's recurrent. Sort of similar and taking over from recurrent neural networks are things called transformers, and they basically turn a sequence to another sequence. So it could be a sequence of sounds turned into a sequence of words. It could be a sequence of words turned into a sequence of words in another language. They're transformers. They're very, very powerful. Embedding layers convert a categorical value to a vector of numbers. So a vector is just a series of numbers. So 1, 2, 4, 6 is a vector of four numbers. You can think of it as an array. A vector implies it's kind of like a single dimensional series. So embedding can be particularly important in natural language processing. You'll come across it, and there are embedders like word2vec, or common other ones are sort of glove, and various things named after Sesame Street characters, it seems. And they might, for example, convert a word into a number or a vector, such that two words that have similar meanings, like big and large, even though they're different words, they will have a vector that is, the two vectors will be very close to each other in value, or in space, if you like. So that's embedding. So embedding layers you'll come across in particularly natural language processing. We're also looking to see whether we can use it to convert things like hospitals into a vector in space, so that similar hospitals that make similar decisions end up with the similar embedding vector. That's exploratory. Encoding layers reduce many inputs into fewer, and that compresses the data, if you like, and then you have decoding layers which can convert it back to the original data. So you may want to just make compression of data for its own sake, or there are other uses of being able to encode and decode data. And then finally, I'll just mention generative data. And rather than our normal networks which are classifying or predicting a value with regression, the aim of a generative network is to produce some form of synthetic data, such as fake images. So if you haven't seen This Person Does Not Exist yet, that's worth having a look at. Can I get to it? This person does not exist. That person does not exist. So that's imagined by a generative network, and it says it's imagined by one called StyleGAN 2. And we're using these type of networks to see if we can synthesize patient level data that we can then share and publish with other people to get around problems of moving confidential data around the place. So we want a data set that looks like real data, real patient data, but isn't. So we're using some of these same techniques here. Okay. Just finally, I'll mention introductory resources. There's a nice video here that takes you through a number image classification problem, and describes the neural network. And that's the series, about 4 videos. That's then leads on to things like backpropagation. All that. It's about 20 minutes long. It's very good. You start to get an intuitive sense of why multiple layers, and what are the multiple layers, and what might they be doing, and he describes it really well. So I thoroughly recommend that video. Right, next stop, let's actually get cracking and do one of these. Okay, I'm back in Colab. It will produce graphs for us, it just doesn't seem to show the images that I put in for explanations of stuff. Right, so we run a cell with the little play button next to it. The first one's a bit naughty really, don't put this in your real work, but it just sort of tidies up, stops warnings coming up saying so such and such version is being deprecated and you need to update to this and that. So I'm just going to turn the warnings off. It'll ask me, do I want to trust my own notebook? Right. Now we're going to load our modules, so we are loading our standard package of matplotlib, numpy and pandas. We kind of use those in everything. Scikit-learn for pre-processing. Oh, by the way, for this I'm assuming everybody has worked through the Titanic version with logistic regression, so I'm not going to re-explain things more than a very passing reference to them. So we're using scikit-learn train test split to split our training and test data set, and we're using min-max scaler to, remember, we standardize our input data. With logistic regression we use standardization. With neural nets we use min-max scaler as standard, which is easy to understand. All of our features get scaled between 0 and 1. Then we're going to input a whole lot of things from TensorFlow, and particularly Keras. So to explain what Keras is, TensorFlow is the neural network architecture developed by Google. Its application programming interface, API, is a little bit fussy and complicated to use. So a chap called Francois Cholet developed Keras, which sits on top of TensorFlow and does most things very easily. So you can simplify your code. You can still dig down into TensorFlow itself if you want to. So this is, and don't worry about what each of these are yet. We'll have a look at that as we go through. So we import our modules. I can't remember whether we've done that or not. Okay. Now, if you're on Colab, it's got to bring in the Titanic data. So this is the same as with the logistic regression. If you're already got it locally, you won't need to download it. So we'll download our data. That's downloaded it from GitHub repository and stored it locally on a Google Colab server. All this is destroyed when we leave, when we close down, or it keeps it there. I think if you went away, I think it closed down automatically sometime between 12 and 24 hours, which it does even if it's running as well. So you have to sort of make sure you're saving your model as you go along, because Colab, the free version at least, does automatically close it down after about 12 hours. So here is our scaling function like we used before, but now we're using min-max scaler. So it scales based on the values in the training set, normalizes everything to that, normalizes the test set to the values of the training set. So this is all as before. We load up our data. Here we're converting all our data. We know it's numeric data already because we've already done that. Convert it all to float. We're going to get rid of our passenger ID as before. Our X, our features, is all the data apart from the survived column. X is equals 1 tells us we're working with columns in pandas. And Y data is just the survived column. So we've got all of our input features, all of our Y features. And then, now I've put convert to NumPy as required for k-fold splits. We're not actually going to use k-fold splits, and we're going to do a single training test split, it is worth looking at the Titanic page on k-fold validation. That's the normal for when you want to know how good your model is. You don't do a single training test split, you use what's k-fold, which means if you've got 5-fold k-fold validation, it will create 5 test sets, and all of your data will be in one test set and only one test set, and then each time the training set is the remaining data. So k-fold validation is something that if you're doing a project for real, you ought to be doing, but we're using a single train test split on this one. Okay, let's set up our neural network, and this text here, which I won't read, I'll just talk through it here. So we have a function to make our neural network. Now this function will build any size neural network, any number of layers you want, any number of neurons. So you can build a massive network with this function, and it uses TensorFlow's what's called sequential method, where we know we're not going to build up anything more complicated than one layer feeding into another layer feeding into another layer, all fully connected. On the Titanic website you'll also see methods for building more complex architectures, but this is a very common architecture, just ordinary sequential. So input, number of features, so that's the number of input features in the Titanic dataset. Number of hidden layers that we want to build, so these are the number of layers between our input and our output. So that could be 1, could be 100. Don't try 100, it won't work for this sort of thing. Realistically, for most things it's going to be between 1 and say 6 or 7 for most classification problems. The number of neurons in each hidden layer I've got as 128 here. Dropout we'll talk about later, but this is set to have no dropout. And our learning rate, so all these are defaults of 0.03 if nothing else is passed to it. So these are inputs. Now the first thing we're going to do is just clear anything that's already there. Probably not needed anymore. There used to be a problem with TensorFlow left models hanging around it on the GPU, but to be safe we clear the session. Now we say we're going to want a sequential neural net, so net is sequential. So this was imported from TensorFlow.keras.layers probably, or TensorFlow.keras. This is the Keras instruction for saying we're going to build a neural net that is fully connected. Now the next one will add, each time it's going to add a layer and then also add a dropout layer. Don't worry about the dropout layer, we'll come back to that. So put this in a for loop, and so you don't need to put things in a for loop. I could just say net add what kind of layer. I want to add a dense layer. This is fully connected. This is the number of neurons in it, which is given up here. So this is a dense layer, fully connected layer with 128 neurons. Input dimensions, it tells it this is the number of inputs to the first layer, and after that it works everything out automatically. Here this is being defined in every layer we build, but it'll only be used by the first layer. So the first layer we tell it number of inputs. The number of outputs will be the number of hidden layer neurons, because each neuron has an output. And then from now on it kind of knows the next layer will need the number of inputs that the previous layer had outputs. Here's where we define our activation. Now if you're using PyTorch, you define the activation as a sort of separate layer normally. In Keras we wrap that into our neural network layer definition. So our activation layer is rectifying linear unit. So this is our most common internal activation. And then in that dropout, in the loop, we say add a dropout. Okay. So this is going to loop through, adding in layers. Now we need to add our final dense layer, so our final output layer. This is dense again, meaning it's fully connected. Everything from the previous layer connects into it. And the 1 is the number of outputs. So for Titanic, I know it's going to be 1. I want a probability of survival from 0 to 1. And we define our activation, so we're not going to use ReLU now, because we want a probability output of one thing. Our activation is going to be sigmoid. So basically we've got a big neural network feeding into what is essentially then a logistic regression function at the end. So activation, if you were doing a normal, let me close that down at the moment. Let me close that. Right. It should utilise the GPU automatically. Anyway, we'll come back to that error message, see if we get it later. So where was I? The final activation is our sigmoid. Then we need to tell it what optimizer to use. Remember, optimizing engines, we came back later, and we're going to use, again, if you're unsure what to use, pick Adam. And then Adam, we need to tell it what the learning rate is, which we've defined up here. With just a word on that, if you're using Adam, you set, this would normally be considered quite a high learning rate for neural networks. Learning rate is basically how much it adjusts itself each update. Other optimizers will require you to be more careful and be more judicious in the learning rate and have lower learning rates, perhaps sort of down to 0.00001 could be with some. And then with TensorFlow we do what's called compile that, which basically is just going to build it. And here is when we tell it the loss, and we're using a binary cross entropy loss because we've got a classification problem, so that's cross entropy, and it's only a single output, so we tell it's a binary. Optimizer is, we've defined up here, Adam, we could have put that down here. And metrics, it can, TensorFlow particularly, it's got some nice stuff for monitoring stuff as it goes along, so we can get it to capture accuracy. And then that function will return that built net. So that's building our network of any size. And we can just sort of check the summary of the model structure. Let me just play that so I've got it. Right. Hopefully that will now know it is using a GPU, because it ought to use a GPU automatically. We're going to create a model sort of artificially. We're never actually going to use this. We're just going to give it an arbitrary 10 input features and print model summary. This also helps show up any problems. So if we do that, so it is building the network and it is now giving us our output, telling us what the layers are, in what order, what the shape are, number of parameters involved. So our total number of parameters in this model is 34,500 parameters. That's basically weights that it's going to optimize on a data set that is much smaller, which is the sort of thing that is enough to bring out any statistician into a cold sweat. We are training a model with many, many, many more parameters than we have data points for. Wonderful. Okay, so we've defined our net. We've built a quick example of the net and looked at it just to make sure that sort of makes sense when we look at a description of it. That was just a sort of dummy net that we gave it 10 inputs because it just made we could have given it 1, 5, anything, just to check its structure when we looked at the structure. And now we'll, as before with our Titanic data, we split, as with a logistic regression, we split our data into training and test sets. So this is using the train test split from scikit-learn. 25% of data goes into our test set and the remaining goes into our training set. And then we scale with the function we defined above, which uses min-max normalization. So if we have a look, I've just noticed here we used here as our input for the training test set, we used the NumPy equivalent arrays. We converted our pandas, x and y, further up into NumPy, and we've used that. Train test split will work on pandas and NumPy. If you're using k-fold splits, that method requires that it's in NumPy. So it's probably good practice to convert your inputs and your output into NumPy arrays. Then all the methods can handle it. So then we scale it, and then let me just insert, how do I put a cell in? Okay, so if we look at our training set, and I'm just going to look at the first 2 passengers. With a bit of luck, all the values should be between 0 and 1. Oh, you can't do Shift Enter. Anyway, just press the play. Okay, so this is passenger 1. This is their sort of input features. So yeah, we'd see they're all between 0 and 1, and similarly on the second one. So that's good. So it looks like our scaling's worked fine there. Let's get rid of that. Okay. The next bit is a little function I've pulled out just because I remember there was more than once that I wanted to do this. So if ever you find yourself repeating lines of code, consider putting it into a function. So this is going to report out the accuracy of the model both on the training set and the test set. So we pass it the model. We pass it training and test X features and Y the actual or observed values. It then gets the probability of survival from the model. This is the TensorFlow model that we've passed it with predict. So predict always gives a probability output. We then say that the predicted class, whether you've survived or not, you have survived if the probability of survival is greater than 0.5. We use this flatten just because the matrix that this comes out with has kind of an additional wrapper around it, if you like. It's within another matrix. It's the way TensorFlows and TensorWorks you don't need to worry too much about that here. But flatten just puts it back into sort of what we expect it, the output expect it to be. It removes one of the dimensions of the array. And then we check our accuracy of our training set by saying, well, first of all, it calculates y predicted train equals y train. We'll get a 1 for each value that's the prediction is the same as, or true, we'll get, sorry, prediction where the prediction matched the actual, and it will be a false where it's not. Python always can handle trues and falses as zeros and ones, or ones and zeros. And so if we take the average of that, as we did in the logistic regression, we get the proportion of training samples that it got right. And then we do the same for the test data. We pass it the test X, we get a predicted probability, we classify based on a cut off of 0.5. We just flatten that to get it back to a dimension that's more easy for us to handle, and then we get the test accuracy. And then we print that. So f strings, if But F before allows us to use this format where we pass it a variable and it will automatically look up the value of that variable, and this one points it to three decimal places. Okay, so that defines our function. Also going to define a function to plot what happened. So it's getting the accuracy throughout the model run. We'll see Keras is doing that automatically for us as well. It's storing in itself, and it's in something called a history dictionary, which we'll come to. We pass that training history dictionary that Keras gives us to this function, and it's going to plot both the accuracy with the training set and accuracy of the validation or test set over time. So you'll see what this looks like. So this is a pretty standard matplot libplot for plotting a couple of things, and it'll give it a title and labels. So we've defined that as in a function. Okay, that's all we need to do to fit the model. So let's fit the model. I'm just going to insert code cell below just to show a couple of things here. So we want to tell the network, when we build the network properly, we want to tell it the number of features. That's the number of inputs into the neural network. Now we can get that from looking at the shape of our training array. And what we see is our training array is 668 rows and 24 columns. So we have 24 columns of data for 668 passengers in the training set. So remember, Python 0 indexed, so the number of features is 24. So this, from its brackets, we can see here this is a tuple, and we can get the second one by putting in index 1. So that should return 24. Okay. Now we build our model, and the only thing we're going to pass it, we could pass it different learning rates on different numbers of layers, which we'll do later. We'll leave it as its defaults. We do just need to pass it the number of features, which we've got, which is 24, and then we're going to fit the model, and we pass it the training data, the training label, y, number of epochs, the number of times it's going to go over the same data, and then our batch size is the number of examples it passes to the GPU at once and calculates the loss based on this. Now, if you're running on a GPU, the bigger that number is, the faster it will run, up to the point where you fill the GPU, which on a data set like this we sort of never will. But you can get not quite so good fitting with very high batch sizes. So Jan LeCun, who's one of the big names in neural nets, he says, though people disagree with him, friends shouldn't let friends use batch sizes of more than 64. So here I've put 64. Then in TensorFlow we can also get it to measure the validation, the test set data as we go along. And we'll come back for both plotting, and we'll come back to how we can actually use that during the model run as well in a bit. And then verbose, do we want it to kind of spew out its progress? So naught keeps it tidy, but on this run I'm going to set that to 1, and then you can see what it's doing. So number of epochs, 250. You start with almost anything. What you want to get to is to see that at least your test set has plateaued off in accuracy. Otherwise put more epochs, train it over the data again. Let's see what this does if we run this. Okay, epoch 1, 250. So it's going pretty quick. If you're running this on locally on a CPU, you'll find it's running. It'll run quite a bit lower. Basically, each time it's giving us the loss. Remember, we calculate a loss. This is the binary cross entropy loss. So it's trying to get this as low as possible, and then it's plotting our accuracy. And our accuracy is the accuracy here that it's plotting is of the training set. If I skip along, we can see validation loss and validation accuracy. So we get our test set accuracy, and already we can see our test set's fitting to over 90% accuracy. Our test validation test set is 76. We'll come back to that. That's all right. That's sort of what we want to be seeing at the moment. We're overfitting this data. So if I show the accuracy, my training set data accuracy, if I pass it through right at the end, is 92.7. Test set accuracy, 76.2. Overfitting. But don't worry. Now, to get a plot, we need to get, when we fitted this, sorry, and now it's all the way up here. So about this. Let's scroll back down to model fit. Model fit. Now we could just write model.fit, but if we write history equals model.fit, then Keras behind the scenes saves a whole lot of useful and interesting information for us. Well, it's useful at least. And we can kind of see what's in that. What we want to get out is what's called the history, which is the training history. And I'm going to put that in a dictionary, because I know it's a dictionary, but I'm going to call it a dictionary.dict underscore history.history. Then I'm going to see what's in it by saying what are the keys in that dictionary. So you'll remember, bit of rehearsal, Python dictionaries have keys and values for each key. So if we do that, our keys are loss, accuracy, validation lot, validation accuracy, which is what it's plotted here. Now I pass that plotting, that history to the plot function, and that pulls these out. It pulls out accuracy, which is our training accuracy, and validation accuracy, which is our test set accuracy. And we can see this is very, very typical of neural net training, that with each epoch, as we're passing our data through, our training set is fitting more and more and more, get better and better and better. It still appears to be going up at the end, over 90%. Our training set data fits, initially it improves, and then it starts to come down. And this is overfitting, which we'll look at what it is and what are we going to do about it. There are various ways of dealing with this. But remember, we want to first produce, in neural net land, we want to produce models initially that overfit, and then we start to pare them down. Because if they're not overfitting, they're probably underfitting, which means we're not getting as much precision out of our data as we could. Okay, so this is overfitting. We've got our training data accuracy going up very high, and our test accuracy going significantly lower. And also we often see this pattern that test increases, then reduces. So it's starting to overfit, particularly as the training set data, as the number of epochs increases. Now let's just, again on Colab you can't see the image. I might not include this in the final note, but I'll just talk through it now. So overfitting and what we call regularization. So if we look at a classification algorithm, and we're trying to find a function, if you like, a dividing line, a complex dividing line that separates red and blue dots here. So we can think of this as two features. We've got horizontal and vertical, and we want to find a function that divides the two. And the green wiggly line perfectly divides this training, this set of data. But if this was our training data, the chances are our test set data, unless the green line really does describe the boundary, there's a precise wiggly boundary like this, that green line is going to cause misclassification in data that wasn't used to train it. So another point in this area here, it will classify as red. When we look at that, we might think, well, actually most of them are going to be blue in this region here. We've just got sort of red dot encroaching in there. So that's overfitting. And the idea that you simplify the model in some way, so you reduce its ability to fit the training data, you reduce its complexity, and you come up with this, say, black dividing line here. That's called regularization. So it's reducing the complexity of the function that's used to classify. And though we actually lose precision or accuracy rather on the training data, because we're now going to misclassify some of these points, we believe that the black line here, the simpler black line here, will actually be a more generalizable classification function. So that's a form of regularization, reducing the complexity of the model in some way. And we can check that. If this green line really is better, then when we throw a test set training data at it, then it will fit well. If the green line is overfitting to the data that's used to train it, then our test set accuracy will be lower. So what might we do? And there's a number of things that we can do. First of all, even though I said we want a model that overfits to begin with, arguably this is overfitting too much. So what we can do very simply here is we can reduce the complexity of the model. So we could go down to 1 hidden layer rather than 3, 32 neurons rather than 64 per layer, and then keep the rest the same. So I'm going to redefine my network just as before, but I'm going to now pass it these values that are going to make it a simpler model, and then I'm going to, it also trained in that time. I had verbose equals 0, so we didn't get the long scrawling output from it, and that's actually fitted. So now if I show the accuracy, training accuracy 88.2%, test accuracy 81.2. So our training accuracy has gone down, our test accuracy has gone up. Still a difference between them, so we're still overfitting at the moment a bit. And so we can see here our training accuracy is still going up. Our tested accuracy appears to keep on going up to about training at 100 and 150. It appears to be coming down a bit. So again, this is another characteristic perhaps of overfitting, that as you train the model for longer, the test set data can come down. So you don't always want to keep on training a model. But we've improved this, and we could reduce the complexity even more if we wanted, would be another thing. The other thing though is, and we'll go back to our, let's have a look at our, this was the initial, so we'll do one change at a time to begin with. So we'll keep it the full fat 3 layers, 3 big layers, 3 layers of 128 neurons. If we look at this training and test set accuracy over time, it appears the test set goes up and then reduces while the training goes up further. So one thing we can do is simply not train it as long. Seems crude, but it's actually a very common way of stopping your training before it starts significantly overfitting. And in this case, what I've done is sort of manually looked at when it appeared to be at its best. We'll come back to a Keras thing we can put in that stops it automatically. So if we redefine our network and then fit it, it's already fitted because now we've only got 25 epochs. So our accuracy training is 87.6, test is 80.3. So this is again better than our original, and if we plot our training history, well, it'll be much shorter now. So here's our training going up and our test set looking like it's kind of plateauing before it starts a big fall. Okay, so we've reduced the complexity of the model a bit. If we've over-engineered it, we can shorten our training history. The other common thing that we're going to want to do, and this is probably the most common way of method. First of all, you don't want a method, you don't want an architecture that massively overfits. Then you want to reduce its training so that you don't go long way past when it is best. But the other method we can put in is something called dropout. What dropout will do is for each training epoch, it randomly sets normally between 0.2 and 0.5, 20% and 50% of the weights to 0. Effectively doesn't use those weights. That is done just in training, and with each epoch it's a different set of weights that it removes randomly. So it is using all of the weights, but it's never fitting them all at once, and this helps prevent the network becoming over dependent on any one set of weights. And so we defined this in the network. We don't have to have dropouts everywhere, but it's quite common to have it after, we put it after each layer, that we could say, actually now remove half of the outputs, up to half of the outputs. In fact, we're going to remove half of the outputs from that layer when training, and it's a different half with each training epoch. Then when it comes to actually getting the real output, you use all the weights and neurons again. So the dropouts only during training, and it's a different random set each epoch. So let's do that. So we've kept everything as before. So again, we've got our full fat layer. We're training for 250 epochs, and we'll see what our output is. And I'll just pause it while it trains it. Okay, that's trained. Let's look at our accuracy. So now our training accuracy is 89.5 and our test accuracy is 80.7. So each of these methods have improved compared to what were we at the start? We were at 76% accuracy on the test set. So we've done 3 different methods, and they have all improved our test set accuracy. They've all reduced our training set accuracy to some extent. Here, so this is the training history, what we've done with the dropout. So we still appear to be going up and then coming down a little bit. So we're still getting some overfitting here with longer training. So what we tend to do in practice is combine those. Oh, I will just mention L1 and L2 regularization. They are there in logistic regression, they're there in neural networks. They tend to have gone largely out of favour. Now L1 and L2 regularization are ways of reducing the importance of weights in the network. Now, they act in slightly different ways. I mention them because you can put them in there and you'll see models occasionally with, and it's saying either L1 or L2 or both. L1 is also called lasso regularization. What that tends to do is suppress a portion of the weights close to 0 or to 0. It effectively removes parts of the network which aren't contributing much. And the more regularization you put in there using L1, the more weights will get suppressed to close to 0. So it's forcing we've still got the same number of neurons and layers, but it's forcing a lot more of those neurons or weights to have very little effect. So it forces a simplification. The other one is L2 regularization, which is sometimes called ridge regression. Regularization, I need to change some of the text in here, which I will. What that does is tend to dampen all of the weights down a bit and puts more into the bias. So it kind of pulls more, the output, everything gets pulled close to the average by that. So L1 picks on a few weights to really suppress, L2 dampens them all down a bit. Not so much used anymore. So let's go on to what we will commonly use in practice, and that's to combine various things. One, make sure our network is not massively over-engineered. Secondly, add dropouts. And thirdly, either observe the training and observe when the test set accuracy peaks, and stop there. So manually putting in the number of epochs. Here it would be close to 25. Or here's a trick that you can do in Keras. Keras builds in what's called early stopping. And early stopping, we gave it, when we train the model, we pass it validation data, and it's going to look at that. And basically it says, when does that peak? Have I got a new best validation or test accuracy? If so, yes, I'll record that. And then there's something called patience, which is how many epochs more will I try to improve it? And here we've got 25. So if our test set accuracy peaked on epoch 10, it would go up to epoch 35. But if it hadn't found a better one by then, it would stop. And then we've got restore best weights equals true. This actually rolls back the network to when it is at its peak. Now, there's a slight technical... In practice, this is good. If you were doing one in the real world, I would always use this. If you're doing it for academic publication, people might say, you've artificially inflated your test set accuracy there because maybe that little peak that you found is due to just a bit of randomness, and you've sort of said that's a real high. In practice, that doesn't matter. Just be aware that the accuracy reports might be ever so slightly inflated, but it won't be significantly. So early stopping is a good thing to put in. We put it in Keras callbacks. So here's the syntax. As with all things, copy and paste. We define our network. So now I've gone for 2 hidden layers. Let's put in 1 and 32 neurons. So simplified it down. I've put in some dropout 0.3, well, I'm going to increase that to 0.5. Tend to use 0.2 to 0.35. Experiment between them. There are a lot of people will kind of stick to a favourite value. Or is that just me who does that? If it's an important model, you will then test these different things. Then fit the model, and we just added a line here, which is callbacks, and we're giving it actually the other thing we've put in here, which can be useful, particularly if you're running a really long model. This is going to automatically save itself, the model, at its best point anyway, and not. So this one will save the best model. Early stopping will make sure it doesn't carry on for too long past it. So putting both of those in, and the way we do that is with this callbacks, and we put them in a list. Again, copy and paste. So if I run that, even though we've said 250 epochs, when we look at the training history, it's going to be shorter because it's only going to go for 25 epochs past when it finds its best fit. So, well, let's have a look. Our accuracy now is training accuracy 84.3, test accuracy 82.1. So that's kind of now quite a respectable amount of overfitting in our model. We've got a small bit of overfitting to our training set, but not very large. But that itself can give us a bit of confidence that we're not underfitting, and we've got our best test set accuracy so far. But we can twiddle with all of these, and then if we look at our training history, we can see it's stopped at about 120 here. So even though, so here we can say train for 1,000 epochs, and you know you're going to go far enough, but because we've put the early stopping callback in, then it won't use all of those. It will only go to when it finds the best validation accuracy, keeps on trying for however long more you say, and if it finds a better one it will reset that's the patience, and then it will stop. Okay, so that's dealing with overfitting. Right, last little bit, tiny bit. You've got big models. Some of these models can take hours to fit. Particularly if you're setting up, you may want to set these things up to change things like number of layers automatically, and just in a big run save lots of different models to see which is best. You're going to want to save that model. You don't want to refit a model to your data every time you're doing it. Even with experiments then on the accuracy of the model, I will tend to fit the models, save those, and then do all the sort of evaluation of the model in a separate notebook, and start by loading up the model. So I fit the model once and then I can keep on reloading it. And it's very easy with TensorFlow, and with PyTorch it's very similar. We save the model simply by using model.save, so TensorFlow has a method, or Keras has got a method for saving it. We give it a name. By convention, the extension .h5 is most commonly used. So that saved our model. Now we can load our model with Keras models load model, and we give it the name. So it's going to save it in the directory that it's in. Now, if you're in Colab, you've got to then export this locally, which I won't be dealing with here. With anything you're running locally, it just saves in the directory that this notebook is running. We can reload it with Keras models.load model, and then we can run that model as normal. So we can predict the probability of survival, and then we'll have a look at that, and then we can get our accuracy. So here we are, saves the model, it's reloaded, it's now using restored model. We've got our probability of survival of the first 5 passengers, and then we can check its accuracy, and it should be the same as the one above because it's exactly the same model, but we've loaded it up after saving. Good. That's it. So now you know how to build neural nets, or all the basics of building neural nets. So go away. If you've got some data you can use yourself on it, play with that. Otherwise, there's the HSMA exercise, which automatically loads another data set up to do with stroke treatment decisions. Have a go with that, and build your own neural net and have a play to your heart's content. Good luck with it all, and thanks for listening.